Assalamualaikum and good day everyone. Today our group will be presenting our project on the insulated bento meal box. Our group consists of 4 members as shown on the screen. In this presentation, we will discuss the following topics. First, the problem, thermal energy decay in food. Second, our new innovation. And next, components of need. And fourth, components of approach. And lastly, conclusion. Without further ado, let's begin with the first topic, the problem, thermal energy decay in food. Alright, let's discuss our problem. The problem is thermal energy decay in food. So what the issue? The issue is standard meal boxes cannot sustain target food temperatures for typical daily use. It's driven by unregulated heat transfer and poor thermal design. So there are some gaps in tropical condition in Malaysia, which is 30 degrees Celsius to 35 degrees Celsius ambient. And for the hot meal, it's dropped from 70 degrees Celsius to below safe 60 degrees Celsius. Eating dissolves in 2 to 3 hours. For cold meals, it rises from 4 degrees Celsius to above 10 degrees Celsius. So bacteria can grow in 1.5 to 2 hours. Total thermal energy loss in 40 to 60% within first 3 hours of storage. And for internal temperature variation is up to 12 degrees Celsius. This uneven heating and cooling creates hot spots or cold edges. So for the physics root causes, first, unimpeded heat transfer, conduction through thin walls and lid seal. There are some free convection currents inside air gaps, and there are some thermal radiation escaping across empty space. And second, no dynamic regulation. All design rely only on static insulation materials with no mechanism to disrupt or redirect heat flow. And third, no temperature equalization. Static air layers trap heat unevenly. And let's discuss real-world impacts. For food safety, temperatures enter the 5 to 60 degrees Celsius is danger zone, where bacteria multiply rapidly. And for the waste, 15 to 20% of packed meals are discarded due to the poor eating quality. And there are some energy waste too. It's repeated reheating uses extra electricity, gas, single-use thermal packaging adds plastic waste. And unmet need. No current solution combines simple mechanical physics with thermal design for long-lasting, consistent temperature retention.
Now, I would like to introduce our innovation, the insulated bento mailbox. This mailbox is designed to keep food warm for more than 6 hours without using electricity. The first feature is the aluminum inner layer. It helps spread the heat evenly, so the food stays warm for a longer time. Next, the mailbox has thick insulated wall. This wall slows down heat from escaping, so the food does not cool down quickly. It also has an airtight locking lid. This lid keeps the hot air inside and stops cold air from entering, helping the food stay warm. Finally, the mailbox is lightweight, easy to carry, reusable, and does not need electricity. This simple design uses thermal physics to keep food warm and make everyday life more convenient.
Next, I will explain the component of need. The need is managing and minimizing the rate of thermal energy transfer from hot food to a colder environment. To achieve this, we apply the principles of heat transfer including conduction, convection, and radiation to reduce heat loss and maintain the food's temperature.
The physics-related need we are addressing is effective heat retention in portable milk containers. So, food stays long for long periods without external power. Two specific physics principles are involved: conduction and convection. Conduction is the transfer of heat through the direct molecular contact in our insulated bento meal box. Heat from the hot food is transferred through the container walls. Convection involves heat transfer through the movement of fluid or gases. This is visible when steam and hot air rise upon opening the lid. These principles are important because they allow us to minimize heat loss naturally. These concepts are very relevant in real life to these situations. On campus, students face long 15 to 20 minutes queues, leading many to choose unhealthy fast food. Campus microwave are limited, often poorly maintained, and create bottlenecks. This results in cold meals, time wastage, and health issues. Problems that can be solved by better applying conduction and convection for heat retention. Beyond students, these principles are important in professional and logistic settings. Office workers often lack pantry space and time to step away from meals. Delivery riders and Grab and Go users struggle to keep home cooked food hot for 6 hours due to poor heat retention. By designing around conduction and convection, the insulated bento mailbox addresses these real-life needs effectively.
Now, let's look at the core design principle of this insulated bento mailbox and how it uses thermal physics to keep your food warm. First, it uses a double wall insulation structure. This creates a barrier between the hot food inside and the cooler air outside. Second, it focuses on minimizing heat conduction. Conduction is how heat travels through solid materials, so the box is built to slow this process down as much as possible. Third, it works to prevent heat loss by convection. Convection is when heat moves through flowing air, so the design stops warming air from escaping and carrying heat away. All three of these strategies works together to cut down the three main ways keeping your food warm for hours. How physics concepts are applied to the bento box? Now, let's break down exactly how conduction and convection are handled in this design. Starting with conduction, heat transfer through direct contact. The layer between the double walls, either a vacuum or foam, act as an poor conductor of heat, so very little heat can pass through it. The box walls themselves are made from materials with low thermal conductivity, which slow down heat flow even further. Next, convection. Heat transfer through moving air. The airtight lid and silicone gasket seal every gap, stopping air from moving in or out and minimizing heat carried away by air circulation. The entire food compartment is tight, sealed, so warm air cannot escape and take heat with it. Every feature here is built specifically to cut down these two types of heat loss. Now, let's talk about the special features that make this bento box even better, which is latent heat storage using material called phase change material or PCM. When you put boiling hot food inside the PCM jacket around the compartment absorb the extra heat energy. It uses this energy to change its state, melting from a solid into a liquid while storing all the heat without getting hotter itself. Then, as time passes and the food naturally start to cool down, the PCM does the opposite. It freezing back into the solid form. As it solidifies, it slowly releases all the storage heat back to the food. This steady heat release keeps the food warm and at a nice temperature for much longer. So the physics formula that explains how this storage works is Q equal to M times L. Let's break down what each symbol means. Q stands for the total thermal energy that is stored or released by the PCM. M is the mass or amount of the phase change material used. L is the specific latent heat of the PCM. This tells us how much energy is needed to change the material's state without changing its temperature.
So what are the benefits of this innovation? Our insulated bento mailbox can maintain food temperature for over 6 hours, allowing users to enjoy one meal without reheating. Since it does not require electricity, it is energy efficient and suitable for students, office workers, and travelers. It is also environmentally friendly because it reduces the need for disposable packaging and repeated reheating. In conclusion, the insulated bento mailbox is a practical solution to the problem of thermal energy decay in food. By reducing heat transfer through conduction and convection, it helps maintain food temperature while remaining portable, reusable, and electricity-free. This project shows that thermal physics is not only a theory we learn in class, but it can also be applied to create simple innovation that improve our daily life.